Hey everyone, Mrs. Pasega here, and today we're working on Unit 10. Remember, if you haven't done one of these recently, you should be doing the entire review packet first, then checking the answer key that's on both Classroom and Drive, and finally watch this video and only focus on the parts you need help with. The front page with the objectives lists the things that you must be able to do for the test. And it describes how I'll ask them too. So if it says, state the names associated with electromagnetic radiation and be able to arrange them in order of increasing energy, then you know I'm going to ask that as a question on your test. Great, so let's get started and we'll use the objectives to check off things as we go. I suggest that once you do the review packet for the first time, you check off what objectives you'll already feel comfortable with. That way, you only focus on studying the things that you're struggling with. So let's start with the electromagnetic spectrum. And for 5480, since you are allowed open notes on your test, this might be something that you decide to do as like on your note sheet here. So we're going to list the electromagnetic spectrum in order from lowest to highest energy. In my head, I always put visible in the center. I'm very human-centric here. We can see these colors of light, so I know it's in the center. And right above violet light is ultraviolet light. Ultraviolet light is ionizing and dangerous, so think of it as it has more energy than violet, so much energy it could knock electrons out of their orbitals, changing the structure of certain atoms and making them bond differently. If those bonded atoms are in something like your DNA, that causes a mutation. But ultraviolet radiation is not as powerful as X-rays. Ultraviolet gets stopped by skin, X-rays go through your skin and flesh and get absorbed by your bones, causing things like leukemia as opposed to skin cancer. The highest energy is gamma. These come from either radioactive sources like naturally occurring elements in the earth, and there aren't that many of them, or in nuclear decay in the sun, right? So these are our high energy ones. Let's go to the other end. Below red is infrared, and we feel infrared light as heat. It's less energy than visible light. Then we have microwaves. And finally, radio waves. Feel free to write this on your note sheet since we're going to need to know them in order from low energy to high energy. Well, low and high energy also correspond to low frequency and high frequency. And if you're wondering why that is, I want you to imagine taking a slinky and shaking it. If you shake it with a very high frequency, you put in more energy in order to make the wave move. So maybe I'll draw that right in this little space. Imagine I've got a slinky and I shake it up and down. If my slinky makes a wave, that frequency being low means my wave is very big. Do you remember doing this with standing waves? If I shake it very fast, then it has more energy put in, so it shakes up and down more often and makes very small waves. When the frequency is low, it made big wavelengths, and when the frequency was fast, it made short wavelengths. So check, check, check. If you wanted to write down a pattern here to help you remember this from later, if frequency goes up, then wavelength gets smaller. But in order to have high frequency, you must put in high energy. You'd have to shake this wave very fast in order to make the frequency big. But notice they all travel at the same speed because this is the same medium. The speed of a wave doesn't depend on its energy, just its medium, which I'll review with you in 2 seconds. So my low frequency end is radio. My high energy band is gamma. They all travel at the same speed, so I'm going to skip ahead to I. They all travel at the same speed, so it should say all the same, not all the same. And that special speed is 3 times 10 to the 8th meters per second. The speed of light in a vacuum is always this because there's no particles in the way. If matter was in the way of your wave, it would travel more slowly. Using this speed and the fact that these are waves, let's calculate some light. So what I'd like us to do is calculate the wavelength of something, and I'm going to check on my equation sheet what equations have wavelength in it. I could use this one. I could use this one. But I shouldn't really use the diffraction and interference one because that only works with the double slit experiment, which is not what I have right now. So we're stuck with just this. A strategy, if you have trouble picking out what equation to use, is to go to your equation sheet and write down every equation with wavelength and just select or cross out the ones that don't make sense. This one doesn't make sense because I don't have diffraction. So let's calculate. I see the speed of light is 3 times 10 to the 8th. It is always that in a vacuum. I'm trying to find wavelength, so I leave that as lambda. And the frequency is 9.25 times 10 to the 10 to the positive 7th hertz. When I go do this division, I'm going to point out a very special thing that you should do. Whenever I see something in scientific notation, I'm going to put little parentheses around it. I'm going to treat that number like a block and never break the parentheses. The reason I say this is because when I divide the 9.25 to the other side, I want to keep everything in parentheses together. So that's 3 times 10 to the 8th over 9.25 times 10 to the 7th. And I'm going to keep my parentheses intact. When I go do this in my calculator, if I forget those parentheses, my numbers come out wrong. So sorry that my calculator is a little bit hard to read here, but let's do this. So parentheses, 3 times 10 to the 8th, divided by 9.25 times 10 to the 7th, close up the parentheses, and this gets a wavelength of about 3.2 meters. This makes sense to me because radios have large wavelengths. They can be as large as a mountain. So having a large scale wavelength makes sense. Light, for instance, has a wavelength that's about a little bit smaller than the width of a human hair. Gamma rays have wavelengths the size of an atom. So having a big wavelength of 3, that makes sense. Next, I see that this question is asking to calculate distance. So let's use this elimination strategy. This equation has a d for distance, so that's possible. This equation has a d for distance, that's possible. I'm going to write down both equations. Then I'm going to read through my problem and see if it makes sense to do one over the other. In this equation, I have time and distance, but I don't have diffraction and interference, so I can't use this. Excellent. Now what do I have for speed is the speed of light. It's still, hey, 3 times 10 to the 8th meters per second. So let's use that. I get 1 point for the equation, 1 point for the substitution, and 1 point for solving. So I want to calculate the distance, and I know it takes 1.255 seconds. Now, if you're a person that has trouble with algebra here, keep in mind that I want d by itself in the numerator. So to get rid of this division, I'm going to multiply both sides by 1.255. Now this reads, with these two canceling, this reads d is equal to 1.255 times 3 times 10 to the 8th. And if you want to keep your little parentheses around 3 times 10 to the 8th, you can totally do that. Because notice, this makes sense to me. light travels 3 times 10 to the 8th meters every second for 1.255 seconds. And that gives me a distance of a big number. Now, choices here. Feel free to leave this exactly as written. So that's 3765 with 5 zeros after it. So 367,500,000 meters. You can leave it like that. If you would prefer to change this into scientific notation, this would be 3.765. And let's count the zeros, or count the places that I move the decimal. I would move the decimal 1, 2, 3, 4, 5, 6, 7, 8, right before the 3. And since I moved the decimal place 8 places, it's 10 to the 8th power. Cool. I'll take either answer, especially if you show me your work that goes along with it. If I used a different type of light, this would still take the same 1.255 seconds. The reason is, it all travels the same speed. And the light's going to the moon and back. It travels the same speed, for the same distance. It's going to take the same time. And the crux of this question is you have to know that even though their energies are different, and their frequencies are different, and their wavelengths are different, what electromagnetic waves have in common is they all travel at the speed of light through a vacuum. A vacuum is a medium where nothing is in the way of those light beams. So it goes as fast as possible, and that special speed is 3 times 10 to the 8th meters per second. So before we go on, let's check our things. You should be able to state the names of the parts of the electromagnetic spectrum. Talk about how light is a combination of many wavelengths. Let's see if we get to that later. Describe that high energy waves come from short wavelength, high frequency, or large amplitude. So we talked about this when we were here. We can calculate distance and time, and we can calculate wavelength and frequency. Beautiful. Let's do some reflection. These are 2 great pictures that would be awesome for your note sheet. The one on the top is diffuse reflection, and this is diffuse because it's a rough surface. Examples of diffuse reflection would include things like this calculator. This calculator is black because when light hits it, all of the colors, all the wavelengths of light are absorbed, but whichever ones are reflected are scattered randomly through the room. This thing's bumpy surface scatters light randomly. So if I were to look at this, I wouldn't see an image of myself. Diffuse objects, you can see the color of the object, like this red marker, but you wouldn't be able to see an image in it. Specular reflection is with smooth surfaces. So S for specular, S for smooth. Specular reflection is when light hits a smooth object, obeys the law of reflection, they actually both do, obey the law of reflection so that you can see an image. Examples would be things like a mirror, a puddle of water, or a really shiny smooth car. Now, the law of reflection is pretty straightforward. Law of reflection says that the angle of incidence is equal to the angle of reflection. So in this case, this would be 55 degrees. And this shows law of reflection because the angle of incidence is equal to the angle of reflection. I'm going to put little geometry equal symbols here so I know that they are equal. The total angle from here to here then, from incident to reflected, would be 55 plus 55 equals 110 total. For this, be able to draw a ray diagram of reflected rays. In this case, all the bits are labeled for you already. but you should be able to draw all 5 parts of this diagram. So you should be able to draw the incident ray, reflected ray, normal line, and both angles. You would get 1 point for each ray, so let's put the incident ray symbol, the reflected ray symbol, R. For angles, to make sure you've got the right one, you first label the normal line, which I normally do as an N, and the 2 angles you care about will literally touch this line. So let's check if we got all the reflection things. We talked about how reflection is when light hits a boundary and bounces off. We can draw all 5 parts of a ray diagram. We can identify a missing angle because the incident will equal reflected, and we know that specular reflection is a result of smooth surfaces. Diffuse reflection is a result of bumpy surfaces. A thing that often happens at the same time as reflection is refraction. The difference is, reflection is when light hits a boundary and bounces off. Refraction is when light hits the boundary and actually enters the new material. When it enters the new material, certain things change. Specifically, the index of refraction, speed of light, and angle with the normal. So now let's calculate speed of light, and I'm going to use, at least verbally, this equation where we calculate speed. And I see there are some options. I could do V as lambda f, I could do V as d over t, or I could use V as 3 times 10 to the 8th over n. This equation makes sense to me because I have n from this chart. So I get a point for writing down this equation. V is 3 times 10 to the 8th over n. Then I get a point for substitution. N of an emerald from this chart is 1.57. So substituting this into my calculator with those helpful parentheses around everything in scientific notation, this would be 3 times 10 to the 8th divided by 1.57, or, oh gosh, again, a big number. You can either write this exactly as it's written here, or do what I'm going to do. Write this as a power of 10. In scientific notation, this is 1.91 times 10 to the 8th. And just to check to see if this number is reasonable, I'm expecting a number that's slower than the speed of light in a vacuum. Because with an emerald, all the little particles and crystals and atoms are in the way of the propagation of that light. It should be slower than it is in a vacuum, but it still needs to be fast, right? Like for instance in this new material. In a new material, I have this fast speed and I want to calculate n. So I'm actually just using the same equation again. There are 2 equations with n in them, but this one doesn't make sense because I don't have any angles. So I get a point for writing down V is 3 times 10 to the 8th over n. Then I'm going to substitute 2.29 times 10 to the 8th. And before I do any math, I'm going to notice that my 10 to the 8th cancels. If I have the same number on both sides of the equation, they cancel out. Rewriting this, now my math is a lot easier. It's 2.29 equals 3 over n. If you don't remember how to solve this algebraically, we're going to use cross-multiplying here. I can switch these 2 digits, or these 2 numbers. Now this reads n equals 3 divided by 2.29. Now I'm expecting in this case a number between 1 and 2.4. So I think I got it. This is n equals 1.31, which makes sense. If I had a number that was too small, let's say I accidentally did my division in the wrong order, that's an unreasonable number. That's too low for an index. because index has to be between 1 and about 2.4. If I accidentally multiplied instead of divided, that number is too big. So check at the end of the problem if your index of refraction is reasonable. From this chart, I see that something with a small index has a faster speed. Something with a large index has a slower speed. This is an inverse relationship, so if the index is large, then speed is small. The largest index was a diamond, it's the upper end of this range. And so in a diamond, the light travels slowest. That's because it has the largest index. A diamond is one of the densest things that you can have that still lets visible light through. So if the index is big, there must be a lot of particles in the way. So there's a lot of slowing down of this light. Just like with reflection, you want to be able to draw a refraction ray diagram. And with this diagram, let's say I have my fishy fish. Light leaves the fish and it goes towards the water, goes towards the air. The normal line is the line that is perpendicular to the boundary between the surfaces. The incident ray is the one that has light going towards the surface. The refracted ray is the light leaving the surface. And the angles go between the ray you just measured and touch the normal line. So just to double check, your angles always have to touch the normal line, including if you have reflection. Notice both the angles are touching that normal line. The normal is the reference line, so it should be touching there. So we have labeled all 5 parts. Check. Now let's use this to get the speeds of things. Whichever material has the slimmer angle is also the material that has the slower speed of light. So in this case, water is the slower material because it has the slimmer angle. Air must be the faster material because it has the fatter angle. As light travels from air into water, from water into air, that must mean the speed increases. When I go from the fish to the air, it is now entering the faster material, it speeds up. If air is the faster material, it must have the smaller index because of that inverse relationship. It must be going from a high index to a low index, so the index of refraction is decreasing. Finally, let's see what the angle does. The angle starts small and becomes big. The angle is increasing. All right, math problem now. Calculate the index. There are 2 potential equations for index. One, where we relate the speed of light in a medium to the index of refraction, or use Snell's law. The ni sine theta sub I equals nr sine theta sub r. I like this equation because this is matching. In air, the index of refraction is 1, and the angle is 42. So as long as both of these match, like the index of air matches the angle in air, then I can find the index of refraction of water. I'm trying to find the index of water, and I know this makes a 30-degree angle. I normally don't do this where I plug into my calculator before solving the problem algebraically, but I do know that people tend to get confused with sines and cosines. So I'm going to evaluate both sine values. Sine 30 is 0.5, sine 45 is 0.707, or sorry, sine 42, so let's do that again, is 0.669. I'm going to replace sine 30 and sine 42 into my equation. Now to solve it, I want Ni by itself in the numerator. So to get rid of this multiplication, I'm going to do division. Divide on both sides by 0.5. This means 0.669 over 0.5 gives me my index. That gives me an index of 1.338. That makes sense because the index should be between 1 and 2.4. Plus, I can just go check. The index of water is 1.33. I did it right. So let's see if we can check off refraction. We did the ray diagram with its 5 parts, 2 rays, 2 angles, and a normal line. We know as the index increases, the speed decreases. Nice inverse relationship there. We did 2 problems calculating the speed of light given the index of refraction, and we practiced Snell's law. Hey, unrelated here, kind of a cool thing. Because a person who might observe the fish sees this ray of light, it actually thinks the fish is ... up here. The image of the fish and the actual fish occur in different places because of refraction. The light is bent, but our brain doesn't know it, so it thinks the fish is there. So last wave property before we get on to particle and energy properties. Diffraction. Whenever you see diffraction, we're dealing with this y equals lambda L over d equation. In this case, the red laser light is diffracting around the wire. When it bends around the wire on both sides, remember diffraction is an example where light either bends around an object or through an opening. Then, the wave that goes above the wire and below the wire now has 2 waves in the same medium. They interact with each other, causing interference. The bright spots of interference come from constructive interference. That's where a crest meets up with a crest, so the waves add together, making a brighter light or a louder sound, or an antinote if we're talking about a standing wave. The dark spots are when a crest meets up with a trough. They cancel each other, and so now you have destructive interference, and that is the dark spots. Now let's use that equation for proportions. This is the distance between the bright spots depends on 3 things. The wavelength, which is a direct proportion, the distance to the screen, that's a direct proportion, and the size of the wire. This is D right here, actually. The size of the object or hole you're dealing with. So I'm actually going to identify the variables first and then write my response. I know that Y is directly proportional to wavelength. So if wavelength goes up, Y goes up, direct proportions. I know if D increases, Y decreases. Those are inversely proportional. And finally, L. If L goes up, then Y goes up. They are directly proportional. Having this equation is nice because I don't have to memorize anything. I can check the equation that I have written down and use this to get my proportions. So if green has a smaller wavelength than red, because this is direct proportion, that means if wavelength is smaller, then Y decreases and the dots are closer together. This creates a rainbow with violet on the inside, green in the middle, and red on the outside, just like a real rainbow in the sky. If the thickness of the wire were larger, the bright spots would be closer together. Y would decrease because of this inverse relationship here. Finally, if the screen is moved closer to the wire, that would actually mean L decreases, so Y also decreases. If L decreases, Y decreases, that also would make it closer together. You've actually seen this with a projector screen before. Imagine like you have your projector screen. And it's making an image of 3 dots. If the projector screen were brought closer, those 3 dots would be closer together now. The closer you are to the source, the smaller L is this distance. If L is smaller, the dots are closer together. Now, you don't have to do any math with this section, but you will have to do proportions. Be able to describe that the interference pattern is bright and dark spots. You should be able to describe that the maxima, the bright spots, occur from constructive interference, whereas the minima, the dark spots, occur from destructive interference. Describe how wavelength, that's lambda, distance to screen, that's L, and the slit spacing, that's D, the size of the small object or the hole you're diffracting around, all change the spacing between maxima. Maxima is another word for the bright spots. They can get closer together or farther apart. Now, we still haven't gotten to the separating the colors of light out to produce a spectrum, really. We talked about how the red laser would diffract farther and green would be closer. I'll pull it up so you can see it. That red would be farther apart and green would be closer together. And that's because if we have white light is made of all the constituent colors, Roy G. Biv included. Because they have different wavelengths, they would have different spacings. It would put red on the outside and violet on the inside, just like a real rainbow. So a diffraction grating separates white light into its constituents colors because they separate out at different rates. That's because white light is a combination of all the wavelengths of light. So now on to our energy and particle properties of light. Where light actually comes from is it comes from atoms that are excited. The ground state of an atom is the most stable state. That's where the electrons would want to go to. You can think of like a bowling ball on top of the hill. On the top of the hill, it has higher potential energy, and that's not a stable state. It could roll down the hill and would want to go to the ground. We label the states n equals 1 is the ground, and everything above it are excited states of n equals 2, 3, 4, etc. Now, this electron wants to go to the ground. It could do this by making this jump down to 4. It could go all the way down to ground, or it could go straight there. This is emission of light because as the electron transitions from the high energy state to low, it's going to put out light whose energy matches here. So my potential energies here, I'm going to get by subtracting. This wave of light that goes from the n equals 3 state to ground should conserve energy. If I take 5 electron volts and minus 2.2, this wave of light should have 2.8 electron volts of energy. This state, so remember I'm just subtracting here, would be 4 minus 2.2. That transition has 1.8 electron volts of energy, so I'm going to draw a slightly longer wavelength for less energy. And the last one is going from 4 to 5. Well, that must put out even longer wavelength. 1 electron volt worth of energy. And those are the only 3 possible energies. So 2.8 was possible, 1.8 was possible, and 1 was possible. The 4, 5, and 2.2 are not possible energy states because those don't represent the differences between this state and a lower, more stable one. From here, this would lead to 3 colors of light with different energies. So let's double check. We know that you can actually skip this top one for me. Doop doop. We know that the electron energy levels are quantized. There were only 3 allowed energies and there was nothing in between. We talked about how different colors of lights, there were 3 colors of lights that were emitted as electrons moved from high to low energy states. We're going to come back to the different elements thing in a second. And we calculated the energy by subtracting. We actually don't need this equation, so cross that out. As long as you can subtract the energy levels in electron volts, you are in good shape, my friends. Now, let's say I go the other way around. I take that same atom and I shine a light at it. This says 10 ultraviolet photons with 8 electron volts each hit this electron. Well, 5 of the electron volts are needed to excite the electron to escape. So my work function is 5. The work function is the lowest energy state. It's because think of it as like, how do we get it from the ground state out? It's got to escape through 5 electron volts of energy. So then, if 8 electron volts comes in and it wastes 5 coming out, the remaining kinetic energy of the electron must be 8. That was what came in. Minus 5 needed to escape. There are 3 electron volts left over. Calculating kinetic energy is as simple as taking the energy of the light and subtracting the work function, because it needs to overcome the work function in order to escape. So each of the electrons has 3 electron volts of light. And there are 10 electrons emitted because there's 10 photons to start. The number of photons, that's the number of little light waves that comes in, equals the number of electrons. So in this case, if 10 ultraviolet lights came in, then 10 electrons emitted. So there are 10 electrons with 3 electron volts each. I just didn't want to draw all of them because can you imagine drawing all those waves and all those electrons? We'd run out of space. Photoelectric effect doesn't work for all colors of light. If there was only 1.2 electron volts, then the electron wouldn't be able to jump out. It would make it to about here. That doesn't even absorb because it doesn't match up with one of the energy levels. This does not cause electrons to be emitted because the incident light, that's this 1.2, is smaller than the work function, the 5. The light energy wasn't enough to overcome the work function, so no electrons came out. So there's a few choices you have to make these the best solar panels possible. Good solar panels should have both fast electrons and many electrons. In order to have more electrons, I need more photons of light. And you could do this in a few different ways. You could increase the solar intensity, you could make the light brighter. Anything having to do with increasing the number of light particles would increase the number of electrons. To make faster electrons, so imagine I want Ke to be really big here, I should make the energy of the light really big. And you could do that in a few different ways. You could have a short wavelength, high frequency, or high energy. because remember, all three of those quantities are related to each other. If you made more energetic light, then the electrons would be faster. If you made a smaller work function, then it would be easier for the electrons to overcome this escape value. More electrons would be able to escape because it would be easier to get out of this little well here. Photoelectric effect is important because this shows light is a particle. And a good picture to have in the back of your head is like a Newton's cradle. One particle of light comes in, and it knocks the electron out of the park. It has a collision, just like a billiard ball would. So the photoelectric effect gives evidence that light is a particle because it can have collisions, one-to-one collisions, where one photon knocks out exactly one electron. And that should be equal for each other. The number of photons should equal the number of electrons because they're having these nice little one-to-one collisions. The more energy the light puts in, the faster the electrons go at the end. And as long as the work function is small, it's easy for the electrons to escape. Remember, you can read the work function from here because it's the lowest energy state. It's the most stable. You have to put in 5 electron volts for the electron to escape. Which leaves identifying different elements by their spectra. We put this under how humans study the universe. I obviously can't send probes everywhere, right? Because it's so far away. We can observe light from distant stars, but I can't ever send things to them. So when we look from light and distant stars, we know that they're going to be made of hydrogen and helium. Stars are made of hydrogen and helium because those are the first elements that undergo nuclear fusion. Lithium, beryllium, carbon, oxygen, nitrogen, those are all emitted or all created later in a star cycle. So from here, how do I get the gases present in the star? I just need to match up the energy levels. So gas A is present, because let's check. This line in A is in the star, the double line is in the star, and this blue line is in the star. A must be there. B can't be there because B's double lines are missing. C's single line in about the orange range is missing. But D must be in there because I see its single line and that double line. One of those must be hydrogen and one must be helium. Finally, we know that all the galaxies are made of stars. The stars are made of all the same elements as ours, right? All the elements in one galaxy are the same matter that are in another galaxy, just separated by big distances. So I was expecting to see exactly this in all the nearby galaxies, and we didn't. When we observe galaxies outside our own, they are almost all overwhelmingly red-shifting away from us. Red shifting goes away, blue shifting goes towards. Since all the galaxies are moving away from ours, that must mean at some point they used to be closer together. So if I draw some stars and galaxies here, the fact that literally every other thing except ours are moving away, well, that indicates that at one point in time they used to be closer together. And if I extrapolate these back towards each other, we can see that they used to be much, much more condensed than they are now. Because everything is moving away from each other, the Big Bang is a credible theory. The Doppler effect for light shows that if the lights are shifted towards red, objects are moving away from us. In the common Doppler picture, sorry that my drawings are horrible, if something is moving away from an observer, that stretches its wavelength out. Having a large wavelength brings those same lines closer to the red part of the spectrum. So I'd still be seeing 1, 2, 2, 3, 4, 5, 6, 7, I'd still be seeing exactly these lines, but shifted towards red, proving that light is stretching out as space is expanding. The cosmic microwave background does this, but even more dramatically. It does this, but instead of just shifting a little bit to the red, it shifts all the way to the microwave part of the spectrum. The early universe was really hot and put out a lot of heat energy that, as it red shifts away from us, is no longer in the visible or infrared part of the spectrum, but now is just microwaves. So the two bits of evidence we see from light, and there are more, but the two that we currently see from light, is we see that the microwave background is the Doppler effect from the light in the early universe. We can see that the universe is expanding because everything is redshifted. And we call this theory the Big Bang, or the expansionary universe theory. That if everything is moving away from us, then it must have been closer together than it is now. That singularity that explodes outwards is called the Big Bang. All right, everyone. So, hey, good luck on your test, and I'll see you soon. Bye.